Okay, we can start now. Um, okay, it's my pleasure to introduce Dr. Hailun Lee today. She's got all academic degrees in energy resources engineering, Stanford University, BS in January 2015, Master June 2015 as well, PhD in 2020. She was postdoc at the here 2020 to 2023, and now she is a research assistant professor in the here PEG since 2023. Her expertise are data analysis and machine learning, geologic carbon storage, multi-phase flow core flooding, and sand tank experiment, reservoir numerical simulation. So today she is going to talk about using sand tank experiment to model CO2 plume migration and trapping. So please welcome and start.
Yeah, thank you very much for the introduction. I hope the mic is on. I'm good. Okay, great. So thank you all for joining me today to listen about how we can use sand tank experiments to model CO2 plume migration and trapping in a geologic CO2 storage. And I'd like to acknowledge all of my collaborators for the work that I'll be presenting this talk. That include my colleagues at the Gulf Coast Carbon Center here at the Bureau, and also from the PGE department at UT Austin, and finally, my colleagues from Australia, so Geosciences Australia and CO2 CRC. And just a quick overview of the agenda today. I'll go through a brief introduction talking about why it's important for us to understand how heterogeneities affect CO2 flow and trapping in the subsurface. And I'm going to present two types of sand tank experiments that are representative of different scales. The first one will be a CO2 flow behavior in and around open fault. So open fault just means it's a high permeability fault. And the second one will be on a CO2 capillary or capillary heterogeneity trapping in realistic ripple bedforms. And finally, I'll just talk about how we can incorporate these sand tank results into field scale simulations via this parameter known as the critical CO2 saturation. So let's get started with the introduction. After we inject CO2 underground, because we have to inject at a commercial rate, which is a high rate, so the injection pressure will be quite high in order to blast the CO2 into the formation. And therefore, in this near well region, the flow of CO2 is completely pressure driven, and the impact of heterogeneity in this area is not very significant. But as the plume migrates away from the well, that pressure gradient dissipates very quickly. So now, instead of the pressure driving the flow of CO2 into the formation, CO2 is now being driven by buoyancy forces, because the CO2 density is less than the formation brine. So it's going to flow upward as it migrates farther away from the well. So now it enters the, instead of being blasted into the reservoir, it's now basically trickling in the reservoir. And at this point, the effect of heterogeneity starts to become quite important. And we call this flow regime capillary and buoyancy dominated. So buoyancy is the driving force driving the CO2 plume upward during its migration pathways, and capillary forces is are the opposing or the resistance force, and these are the forces, capillary forces, that are responsible for trapping or attenuating the upward flow of CO2. And therefore, we call these heterogeneities capillary heterogeneities for that reason. And like I mentioned, when the pressure-driven flow, with pressure-driven force is not important, we start to really see the impact of geologic heterogeneities on CO2 plume migration behavior, as can be seen in these two simulation studies. So here we have heterogeneities on the hundreds of meter scale. So these are interbedded sand and shale. And you see that with the decreasing net to gross ratio, how the shape of the plume is significantly altered. And also we have here a centimeter scale heterogeneity. And still, you see that when comparing simulations between a homogeneous versus a heterogeneous reservoir full of these centimeter scale heterogeneities, you can see how the plume migration pattern is also significantly impacted. And furthermore, these kinds of geologic heterogeneities can cause trapping of CO2 by capillary forces. We call these either residual trapping or capillary trapping or capillary heterogeneity trapping. And these all refer to trapping by capillary forces. But in these, in the sand tank studies, we mainly focus on capillary heterogeneity trapping, or the one that's shown in this core flooding experiment right here, when we have these barriers that can trap the high amount of mobile CO2 behind these capillary barriers. So then the saturation of these trapped pools of CO2 is much greater than the amount of trapping that you would expect from pore scale snap-off residual trapping. So we call these capillary heterogeneity trapping. And these are CO2, this is CO2 trapped by these capillary barriers. And previous study, or these core flooding studies, have shown that it can indeed trap a significant amount. So we're interested in using sand tank experiments to study exactly how all of these kinds of heterogeneities affect a CO2 migration, and how much trapping we can get in different kinds of these heterogeneities. And the way we do that is by conducting two different kinds of sand tank experiments. The first kind, in order to study small-scale heterogeneities or the impact of small-scale heterogeneities, we use the sand tank at its original meter scale. So you see here, it's a 0.6 meter by 0.6 meter, or 23 inches about across. And the tank is very thin, 1 to 2 centimeters thick, so that we can shine light through and then see exactly what's going on inside the tank. And the heterogeneities that we're studying in this type of sand tank study is from centimeter to decimeter scale. So these are small scale, realistic bedform kind of heterogeneities. And for the second type of experiment, in order to study the effect of large scale heterogeneities, we can treat the sand tank as a shrunk field scale analog model. So then in this way, we can model larger scale heterogeneities, such as a fault or anticlines or interbedded sand and shale that are at the hundreds of meter scale. So then we can, using these kinds of sand tank experiments, examine how much trapping we can get with different types of heterogeneities, and how plume migration pathways is affected by these kinds of heterogeneities. And there are many benefits of using these kinds of sand tank experiments to investigate CO2 plume behavior. They capture real physics, they can validate or even complement flow simulations, and these are low-cost experiments with quite large domain sizes that allow us to freely customize domain with different kinds of engineered heterogeneities. We can freely adjust the kind of surrogate fluids and injection scenarios that we use. So using these different fluids, we can model the injection of either gaseous CO2 or supercritical CO2. Finally, we also have high-resolution imaging that offers us direct visible ground truth, so that allow us to use these data set to validate and improve flow simulations. And in order to run a complete sand tank experiment, first we pack the sand tank with any kinds of engineered heterogeneities that we want, then conduct the fluid flow experiment. Each experiment lasts about a week to conduct. Finally, we extract these high-resolution images and post-process them in the computer. And here you're seeing a false-colored CO2 saturation map that can quantify the amount of trapping and also the plume pattern within the sand tank. And now we come to our first example project. So I will start with the kind of sand tank that looks at larger heterogeneities. So these are shrunk analog of the field scale. And just a little bit background for this study. We're interested in looking at faults, especially open fault or high permeability fault, because they present potential leakage risks for CO2 storage projects. And because fluid flow in and around faults are not very well understood, so the Australian teams, they want to conduct a shallow CO2 control release field experiment at the CO2 CRC Ottawa International Test Center, I think this year, because they like to better model, predict, and monitor this fault leakage behavior. And so they intend to inject gaseous CO2 into the Brombees fault. So the Brombees fault is a very well-characterized fault. It is shallow, high permeability, near vertical strike slip fault. And here's a cross-section showing what the fault looks like. So here, this curved feature is the fault. And then here, these two straight lines are two observation wells that have been drilled through the fault. It is a very shallow fault. So this is basically at the ground surface. And that's an advantage because it allows them to deploy monitoring devices on the surface to try to monitor the injected plume. And the injection plan is to drill a well here 60 meters below ground surface and inject to the left side of the fault. So in order to ensure the success of this project, the Australian teams have conducted field scale simulations, as you can see here, because it's very important for them that the injected CO2 from the well actually migrate into this fault, because if it doesn't, then all of their deployed monitoring devices will not be able to detect the plume. Conventionally, after you've conducted the field scale simulations, the next step will be directly proceeding to the field project, because there is no other way to validate these simulation results. But here, we're proposing an intermediate step, which is to conduct sand tank experiments in order to validate and perhaps complement their simulation results. So what I did here is that I extracted a 2D cross-section from their 3D geologic static model, printed it out, and then glued it to the back of my sand tank, and then manually packed this high permeability fault and all the surrounding layers by mixing different grain sizes of glass beads in order to best mimic the permeability contrast in between these different layers. And as a result, here you see the sand tank domain for experiment number 1. And notice that for this very first experiment, we packed the layers all the way out to the edges of the tank. So as a result, we have essentially closed boundary conditions at the edge, the left and right edges of the tank. We then packed 3 more different sand tank domains. They have slight differences. For example, these 3 are different from experiment number 1 because now the left and right hand edges have these high permeability conduits. So now effectively we're modeling open boundary conditions at the left and right edges. And also the latter two experiments now have layered heterogeneities within the fault instead of just homogeneous fault for the first two experiments. And here you see different experiment numbers on top of each domain. This just shows that essentially two experiments were done per domain. So we're able to repeat some of these experiments using the same packed domain with different analog fluids. So just to show you what steps we go through for after we've packed the tank. So next step is to fill it up with the wetting phase fluid, which is usually water, but with other analog fluid, it could also be a glycerol water mixture. And after the tank is completely filled with the wetting phase fluid, now we're able to conduct the actual injection or drainage experiment. We usually inject at a relatively low rate, so 0.2 to 2 or 20 milliliter per minute. And the injected fluid could be air, CO2, or heptane or sulfur 220, which are just different kinds of oil. So air and CO2 model gaseous CO2 injection, and the heptane sulfur 220 oil model supercritical CO2 injection. And all of these experiments are conducted at atmospheric or ambient conditions. And for boundary conditions, we have a constant rate at the bottom inlet and a constant pressure at the top outlet exiting into this constant head reservoir. And now let's look at our first set of experimental results. So here we're comparing experiment number 2 with experiment number 1. So we start injecting air into this water saturated domain at 0.2 milliliter per minute. And we can see that the injected air enters the high-permeability fault through the pulsating finger kind of flow path. And now we increase the flow rate to 2 milliliter per minute. You see again this pulsating finger kind of flow until it hits the top of the fault and now starts to backfill and finally enters this high permeability layer that's brighter than the rest of the domain because it has the highest permeability and lowest capillary entry pressure. And now let's compare it to experiment number 1. So now we have 2 milliliter per minute injection rate. And you see is essentially very similar to the first experiment. And now we increase it to 20 milliliter per minute. So you see still finger-like flow path, backfilling, all very similar. And it fills a lot more in this case because of the closed boundary condition. But otherwise, we see that increasing the flow rate from 0.2 to 20 milliliter per minute, which is a 1,000-fold increase, in fact, does not greatly change the overall flow pattern. And for our second set of experimental results, here we're comparing an experiment with the homogeneous fault versus a heterogeneous fault. And we've already seen this result, the homogeneous one from the previous slide. So now let's focus on the heterogeneous one. So these two are at similar flow rate, but we immediately now start to see the impact of these capillary barriers on the injected airflow, and especially right here at the top. So instead of entering the fault, the top of the fault first, it now actually directly exit the tank through this high permeability layer. So from these two experiments, we can observe that adding heterogeneities to the fault has significantly changed the flow behavior. And for our third set of experiments, here we actually use 3 different kinds of analog fluid pairs. The first one is air and water, and we've seen this result from the previous slide. So the other two is heptane and social 220, and we use these two kinds of oil to model the injection of supercritical CO2. So for heptane injection, we can observe that initially the flow pattern is almost exactly the same as air injection. However, because the injection time period for heptane is much longer than for air injection, so eventually we do see this breakthrough to the top of the fault, and you start to see some backfilling. But if we look at the social 220 case, we can immediately observe a marked difference in the plume behavior. So now you see the injected non-wetting phase invades a lot more of the pore space, which means it has a much greater sweep efficiency. But overall, if we compare all three of these flow scenarios, we can see that they all enter into the high permeability fault, and they all essentially exit out of this domain through this high permeability layer. Therefore, supercritical CO2 flow behavior at a greater depth should still be similar to this injection of a gas phase instead of liquid or supercritical phase. And finally, we come to our last set of experimental results. So this is comparing air injection versus CO2 injection. And we can now take a look at how dissolution effects will actually affect CO2 plume migration. So again, this air experiment is the same one that we saw from the previous slide. But let's take a look at the CO2 injection. We see that the migration of the plume is much slower than the air case, which is not surprising because at this low rate, 0.2 milliliter per minute, the dissolution is quite significant. And we also observe a thinner plume in this high permeability layer and also less saturation overall. So the conclusion here is that dissolution does have an observable impact on gaseous CO2 flow and would delay plume front migration speed. So overall, if we compare these Santan experiments with the actual field scale simulations that the Australian teams have done, we can observe a lot of similarities. For example, there's a high chance that the injected gas will indeed enter into the fault zone, and high saturation can be expected near the injector, within the fault, and in this high permeability layer. But there are also differences. For example, by adding heterogeneity to the fault, it can alter CO2 flow path, and that can actually inform how you would like to monitor plume breakthrough at the ground surface. Because instead of expecting the plume to break through first at the top of the fault, now it might actually break through this high permeability layer first. And finally, by using different analog fluids, we're able to investigate how supercritical CO2 injection will look like. And they are likely to be similar still to this near surface fault flow behavior with just gaseous CO2 injection. And now we move on to our next set of experiments. And this is now looking at small scale heterogeneities. So here on the left-hand side, you see all these different kinds of realistic sedimentary bedforms that you see in nature. So both in outcrop and also in the subsurface. And the question here is how can we accurately model the effect of these realistic bedforms in field scale simulations? So the first step toward doing that is by conducting sand tank experiments so that we can quantify exactly how different types of small scale heterogeneity will affect CO2 trapping amount. And then by incorporating that data correctly into field scale simulations, we can then have hopefully more accurate field scale simulation results. And by using this automated and programmable packing system in-house, we're able to produce geologically realistic bedform patterns. Here on the right-hand side, you see models of realistic ripple bedforms that you can see in nature. And these are called Ruben models. So we model our sand tank ripple domains after these Ruben models so that we can be as realistic as possible in a controlled manner. And here is an animation showing how the automated packing machine is able to construct such a realistic domain using gravity segregation of the mixed glass beads. And here is a lot of the ripple bedform fluid flow experiments that we did all at a glance. And one thing that we can immediately observe is that all of the plume migration patterns and also trapping amount are different due to the difference in these different types of heterogeneities and grain size contrast. So let's take a look at our first set of experimental results. Here you're looking at 4 different types of ripple bedforms. And we can observe that even just slight changes in ripple bedform patterns can significantly impact CO2 trapping amount. For example, the difference between A, B, and C domain is just the whether the ripples are in phase, slightly out of phase, or climbing ripples, and finally completely out of phase. And you can see the trapping amount vary from 4% to about 13%. And this just means that 4% of the pore space is filled with the non-wetting phase or CO2. So it's not just the type of heterogeneity that matters, but also the degree of heterogeneity. And here, by increasing the grain size contrast between the matrix and the laminar faces, we're able to increase the degree of heterogeneity. And we can see that for this single type of ripple heterogeneity, excuse me, by increasing the degree of heterogeneity, we can see an increase in the trapped CO2 amount from 0.4% all the way to 4%, so tenfold increase. And if we compare the trapping amount of the ripple bedform to the cross-laminated bedform, we can now observe even larger difference. So for a cross-bedded case, we can see that the maximum trapping amount is almost 40% compared to just the ripple lamination case, which is only about 4% at the same grain size contrast or degree of heterogeneity. And that's why identifying the correct facies with different sedimentary bedforms is important for this reason. And finally, for our last set of experimental results, it's not just the type and the degree of heterogeneity that matters, but also the wettability of the bedforms. So by wettability of the grains, I mean the surface properties of the grain. So if it's more water wet, it means that water tends to stick to the surface of the grain more than CO2 or oil, which is the non-wetting fluid. And by measuring contact angle, which measures the degree of heterogeneity, So the smaller the contact angle, the more water wet the domain is. So now we see that as the contact angle increases, which means that the domain gets more and more oil wet or has more affinity to CO2. And this is for the matrix phases only. So the laminar phases, which are these darker lines here, they always remain water wet. So they will always be effective capillary barriers. And we see that as the matrix phases gets more and more oil wet or CO2 wet, we observe this increasing trend in the amount of CO2 saturation that is trapped. Therefore, in conclusion, it is important to correctly characterize not only the type and degree of heterogeneity, but also the wettability of a facies. And here we see just a summary plot of all these three sets of experimental results that I just showed. So now that we have all of these different sand tank trapping results, how can we incorporate these results into field scale simulations? And that's the next section I'm going to talk about. We can incorporate these sand tank results via this parameter called the critical CO2 saturation. And the critical CO2 saturation is the first non-zero value in both of these curves. And these curves are relative permeability and capillary pressure curves. And these are input fluid flow models for multi-phase flow into flow physics reservoir simulators. And just to talk a little bit more about exactly what critical gas saturation is, let's look at this example. So here we have a vertical core, and CO2 is buoyantly migrating through the core from the bottom to the top. It's showing green. So here at pressure P1, we see that only a little bit of CO2 is invading the pore space. And as a result, CO2 saturation is very low in the core and water saturation is very high. But then at pressure P2, here we see that CO2 has overcome more of the capillary pressure required to invade the pore space. So now it's evaded more of the pore space and it successfully breaks through the top of the core. So this breakthrough pressure, we call it either the threshold capillary pressure or the capillary entry pressure of this entire core. And the corresponding saturation is what we call the critical gas saturation. And this saturation is important because only until CO2 has reached this saturation can it then form a continuous flow path within this core, so then it can flow to the next section of the core. And if we treat this entire core as a grid block, then this saturation is the saturation that's needed to fill this, to establish this connected flow path within this grid block, so then it can start to flow into the next grid block. So now that we've seen what this critical gas saturation is, our next step is to see whether this is an important parameter to be upscaled. So we want to conduct some field scale simulations to see whether this parameter is important or not. Because if it's important, then we definitely need to correctly upscale this parameter. But if it's not, then it will be safe to ignore this parameter. So for this simple field scale simulation, we only use one geologic model. As you can see here, the yellow represents the sand facies, and the blue represent the shale facies. And here we're conducting 3 different injection scenarios, C1, C2, and C3. So hysteresis just means whether we have residual or snap-off trapping when the water imbibes back into the CO2 plume. And Yeah, and we also investigate whether we have dissolution effect of the CO2 plume or not. So C3 is likely the most realistic case in reality, with both hysteresis and dissolution implemented. But C1, without either of these added effects, we can have a more direct observation of whether or not critical gas saturation is important. And here you can see the simulation results. So in each row, we have the C1, C2, and C3 scenarios. And from left to right, we have critical saturation increasing from 0.1, which is 10% the pore space, for a grid block, all the way to 0.4, which is 40%. And immediately, you see that for all of these three scenarios, increasing the critical saturation definitely has a significant impact on both the plume migration extent and also the plume saturation itself. And here is just more plots showing you quantitative measures of exactly how much the plume lateral migration extent has been reduced with the increasing critical gas saturation. And by increasing critical gas saturation from 0.1 to 0.2, we can see that it greatly reduced the amount of free CO2 in the system. And then it also increased the amount of residually trapped CO2, but then reduced the amount of dissolved CO2. So as critical CO2 saturation increases, we can see a trade-off in between the residual trapping mechanism and the dissolution trapping mechanism. Therefore, from this simulation study, we have concluded that critical CO2 saturation indeed is an important parameter. It can significantly impact both the spatial distribution of the plume and the contributions of the various trapping mechanisms. So our next step is to try to get to more accurate upscaling of this parameter. We plan to conduct more sand tank experiments so that we can have more validated data experimentally to build a geologic phases library, so that for every phases that we identify for at the field scale, either using well logs or core extraction, we can then assign the correct trapping amount to that phases. So then we're able to more accurately upscale these phases dependent critical CO2 saturation values to enable more accurate field scale simulation results. And that brings me to the end of my talk. The main takeaways is that we can use sand tank experiments to model CO2 plume migration and trapping. And then we can use these sand tank models either at their original sizes or treat them as shrunk analogs of the field. And they model real physics and can offer valuable data to validate and improve simulations. So if any of you is interested in collaborating on these sand tank experiments, please let me know. And now I'm available to take any questions you have. Thank you.
Thank you for your talk. Q&A session.
Thank you. Nice work. I love seeing actual physical experiments tied to the real world. Do you control temperature across your sandbox experiment?
No, so because it's conducted at ambient conditions, essentially whatever the ambient temperature is, that will be the temperature of the experiment.
Okay. I'd be interested in talking to you about if that's possible to do, because the buoyancy drive could be an additional important factor in this due to temperature gradient in the real world.
Yes, that's definitely a very good point. And I would love to explore more in that direction. So how you would incorporate example, thermal effect, right, in these kinds of experiments. Yeah, I'm not aware of any other groups doing it currently, so I think it will be quite a novel thing to add to these kinds of experiments.
There's also in my field a lot of interest in it's called CO2 plume geothermal, where you get natural driven buoyancy drive in a reservoir of CO2 to bring heat up to the surface. So, and you can analyze that probably in this case with doing a Rayleigh number calculation to see if you're going to get buoyancy drive or not.
Yeah, that's a very interesting point, actually. Yeah, so I think exploring this synergy between CO2 storage and geothermal extraction, I think, yeah, it's a very interesting topic. And I would love to explore more in that direction, if possible, in the future. Yeah.
Any other question?
So Hailun, you know what I love this stuff, but I keep wanting to explore everything in this we do in Sand Tank has always been vertical flow. But we know from, well, for example, Alex's talk yesterday that KVKH can be quite small, and that the plume spread and the risk may be mostly lateral flow, which I think bedforms, all this bedform stuff is going to have a really important impact also on lateral flow, but it may not be the same impact. I'm really curious about, and I don't even know how you set up a tank that's addressing the issue of lateral migration when underneath a zone that's confining, and most of the migration goes. I mean, you see this in all these tanks, and most of the migration goes out the side when you get a chance.
Yeah, that's a very good point. And I have two points in reply. The first one is, yes, for lateral migration, it's definitely an important aspect to investigate. So for example, all of these heterogeneities, they're very effective in blocking vertical migration of the plume. But a lot of the times when you have these horizontal layers, for example, in this high perm region, you do see the plume extending over a large area. And we can, in fact, investigate this kind of lateral plume migration with a vertical tank, like, for example, in this open fault case. But we will probably want to have a pretty long tank in order to investigate that. And one other experimental setup that I'm currently working on for the sand tank is to have horizontal tank setup. So these, the current experiments are all conducted in a vertical tank, so they're exactly 90 degrees. But with the horizontal tank setup, we can tilt the tank at whatever dip angle that we like. And then by adjusting that dip angle, we can hopefully see how that will affect lateral migration and plume spreading in those cases. So that is very much a next direction that I'm currently actively working on. Yeah.
So there are two couple of questions in chat. John Pantano, if you don't mind, could you please turn on your microphone and ask your question? If not, I can read.
A wonderful talk. Thank you very much. My question that I put in the chat mainly said, how do we take this information where we're going gaseous and unconsolidated to learnings that we can look at the heterogeneity at the deeper systems where we would be doing our full scale application? Thank you very much.
Yes, no problem. If I understand it correctly, the question is asking, because the sand tank experiments are conducted in an unconsolidated bead pack, how can these results be applicable to deeper subsurface?
That's correct. Also supercritical versus gas phase.
Yes, and also supercritical CO2 versus the gas that I'm currently using. Okay, yeah, so that is another good question. And the way we address these, what we call scaling issues, essentially we conduct these lab scale experiments at a smaller scale, and how would it be applied to a much bigger scale at the field? The way we do that is usually by adjusting the different dimensionless numbers or scaling groups to make sure that when we conduct these experiments, for example, these permeability contrast in the field can be represented by the contrast between capillary entry pressure in between these different layers, so that we can mimic that kind of permeability contrast to the best of our ability in these kinds of sand tank experiments. And then for the fluid, in order to be representative of the supercritical CO2, we use these analog fluid, so heptane and sulfur 220, and we try to adjust the density ratio between the wetting and non-wetting phase, and also the viscosity ratio and the interfacial tension of these fluids to be similar as possible to what you would expect for supercritical CO2 and brine at the subsurface conditions. And finally, for injection scenario, so the rate that we use here, and also according to the interfacial tension and the grain size, we also calculate the capillary number, which represents the forces ratio between viscous forces and capillary forces, and also buoyancy, bond number, excuse me, which is the ratio between buoyancy forces and capillary forces. And we want to make sure that these dimensionless numbers are at a similar range from this lab scale experiments to what you would expect at the field scale at subsurface conditions. So yeah, so those are basically the various dimensionless numbers that we calculate in order to ensure that these kinds of laboratory experiments are as representative as possible for what you would expect in the subsurface.
Okay. So another question, Abuja, can you turn on your microphone and ask your question? No, I can read. How can the permeability and porosity of the given layer be measured and changed if needed during the construction of the physical model?
So how do we mimic the permeability contrast using the glass beads? Is that correct for the question? Okay, I assume that's correct. All right. So the way we do that is by using the leverage J scaling function, which takes into consideration porosity and permeability into capillary entry pressure of the different facies or different layers. So in the field, they measure all the porosity and permeability of these different layers. And then in the lab, we have the capillary entry pressure of the different glass beads with different grain sizes. So in order to mimic the permeability contrast by doing a conversion, by converting that into the capillary entry pressure contrast, we can then mix different grain sizes of glass beads with a certain ratio, so that we do a linear interpolation in between the capillary entry pressure of the two pure grain sizes of glass beads, and then mix them to get the desired capillary entry pressure for each of these layers, so that the capillary entry pressure ratio in between the layers should be as representative as possible for the permeability and porosity contrast in between these layers. If that makes sense, yeah.
So any other question in this room?
Thank you for the talk. Your figures are really, really beautiful.
Oh, thank you.
I'm not familiar with the sandbox model, so my question was about, in this figure, for instance, you've beautifully demonstrated the heterogeneities within your bedding how things are packed impact your injection pathways. I was wondering if there was any interest in how that would be applied to the fault gouge, the heterogeneities within the fault rock itself.
Yes, that's another good question. So here we're trying to address the heterogeneity within the fault by building these kinds of simple layered heterogeneity. But I understand that in reality, this is probably not super realistic for what you would expect for a truly heterogeneous fault in the subsurface. And as far as I understood, a heterogeneous fault could have a low permeability core with high permeability damage zone around it. So the true heterogeneity of the fault is likely to be more along the vertical axis instead of the horizontal axis. So definitely in the sand tank, we can construct that kind of heterogeneity for a fault. And in fact, a recent, another group, which is recently published sand tank experiments called the fluid flower, they also use the sand tank as a shrunk analog model of the field. And they have anticlines and heterogeneous fault within their sand tank. And their heterogeneous fault has some vertical heterogeneity within it. So then I think for our next steps to model more accurate fault heterogeneity, that's definitely a direction that we can go toward. And also an even further out idea is instead of packing these tanks manually, which is currently the state of the art, we are thinking of perhaps using a tank, a deformation tank that can be pulled or compressed so that you can, instead of manually producing these faults, we can then produce more realistic looking fault. So that could also be another direction to go for realism for fault heterogeneity.
Nice, thank you.
No problem.
So any other question? Any other question in chat? No question. So no question anymore. So thank you very much today talk. Thank you.
Thank you.